not do real-time data analysis or real-time data accumulation also. This is something that has gone beyond our, I mean, which is humanly possible. I think we need some help there. So for that reason, that is one of the reasons we need these kind of sensors. Then for reduced error and improved accuracy, like where we can eliminate the error and make a better decision based on a lot of data. So a data-based accuracy measurement and error reduction, that is also another huge important point for these sensors. And as we all know that for the environmental regulation committees and from the government also, we need to comply with some regulations. So for that reason also, this kind of smart sensors come very handy. And as we are, we are supposed to be supposed to be looking at the conservation of energy in today's world. And that's why we should look at the smart sensors or the design of the sensors to be more energy conserved or more energy efficient and resource efficient so that it does not consume themselves a lot of data. That should also be kept in mind. So especially in hazardous areas and the areas where human cannot reach or it is very dangerous for human intervention, we need these sensors to be deployed. So the protection in dangerous areas and real-time data collection and also logging and also the sensor output from those areas, these are important for making or being interested in, let's say, smart sensors for environmental monitoring. So this is a very simple block diagram for smart sensor architecture where it starts with the sensing element. So I'll also have another slide basically connecting this slide where we have a physical phenomena and that phenomena is converted into an analog signal with the help of the sensing element. This is the basic sensor principle. So it can be a chemical signal or a biological signal or an electrochemical signal which is sensed by this element. So this is an analog signal which is then changed by amplifying it or filtering it based on the current or the need, based on the need or the requirement of the sensor. Then it is digitized with the analog to digital converter, and then comes the smart part, which is the edge computing. Edge computing meaning we can also do the computations or the required algorithm interventions within the device itself. So it also involves feature extraction, classification, and calibration and quality control. So then comes the connectivity. So what calibration data or measurement data we have found, it goes through a connectivity device like Bluetooth or Wi-Fi or long range device, and then it goes to the output, which provides us the alert or reports. So the app or cloud is also an option. And for making the edge computations, we need some other, I mean, this can be optional for some sensors, but for most of the sensors to work the desired way, we need these auxiliary sensors like temperature, pH, and humidity so that we can do drift cancellation and baseline understanding or baseline calibration and so on. And another very important, I would say, element for the architecture is the power management, because I already mentioned we should make sure that our sensor does not consume a lot of energy themselves. Then in the long run, this is not going to work because we are trying to conserve our planet. Like then it goes against what we started our work for. So basically, we can say now that, okay, smart sensors come with these three things like sensing, it comes with analytics and connectivity. So to reiterate my points, these are the 5 stages of smart sensor working. So we have the signal from the transducer. It can be chemical, optical, bio, or electrochemical. So it is converting the environmental physical phenomena into the electrical signal. Then comes the conditioning, like amplifying or filtering, and the conversion into a digital signal. And then comes the modification, or you can say the extraction of features. By features, I mean a numerical value based on that digital signal, which is, or analog signal also can be used for the numerical value, which will be used for the feature extraction, or which can be used for making the decisions inside the AI component or the smart component for the automatic drift cancellation or automatic noise removal, all these things. And then comes the interpretation, which also involves this calibration and just a moment, calibration, regression, and classification part. So this 3 and 4, these 2 steps are the smart steps that makes the sensor smart. And then comes the output, as I have already mentioned. So before we move forward, I would like to talk a little bit about the application, like very shortly. So if we look at the water quality, mm, just a moment, I need to, can I, just 1 second, please. Yeah, so if we go to the water quality and treatment resource management, so what are we measuring? We are measuring the chemical or biological indicators. So it can be the contaminants, it can be the PFAs, which are basically the contaminants. And where is it important? The treatment plants and mining, process water, and distribution points, these are important. And what kind of decisions it makes. So, with the help of these sensors, we can actually make decisions about process control. It can also make decisions about periodic sampling and also discharge compliances. So all these things can be managed with the help of these sensors. So these are essential in these cases. So what are the use cases for industrial safety and emissions? This is very important for leak indicators, hazardous releases, and emissions. This is also in today's world, I think this is one of the most important sensors. And where is it important? It is important in plants, refineries, and warehouses. And also, we can make this kind of decisions like rapid incident response or worker safety related responses, um, providing alerts to the workers. It's also very, very essential. Now we go to the smart building. So this is again, I think this is very common all over the world nowadays, that we have air quality measuring sensors in our home, like CO2, humidity, temperature, CO sensors, VOC sensors. These are very common. So inside closed rooms and classrooms, I think it is good. And for this kind of optimizations, we can make the decisions with the help of this census, especially in Western countries like in Germany. We have the huge problem of mold. And I think for mold risk mitigation, this kind of smart sensors would be very good. I think I should also have one in the future. So now comes the smart cities. So for CO2, NO2, and particulate matters measurement, we need this kind of sensors. So in roadsides, in schools, such places can really make use of these sensors for hotspot identification or providing alerts for exposure. We can also look at some additional use cases. For example, agriculture and farming, because this smart sensors nowadays we also have seen that drone deployed sensors are measuring soil moisture, temperature, pH for water conservation and yield improvement and fertilization optimization and so on. So another very important use case is natural disaster warning. So it can detect these conditions which can cause as a which can work as a precursor for flood or fire. And so for rivers and forests, these are the areas of deployment, and it can provide us with some early alerts or risk mapping also. And last, very important, last but not the least, which is the waste management. I think also very essential, because I think one thing where human intervention can be reduced with the help of sensors, and that would be very nice, is the waste management. So if we can detect the bin fill level and location or collection status for overflow uh, prevention, and especially for industrial waste, that would be essential. That would be very good. And that is what is, I think, the current norm in most of the cases. So now we go into the recent research into some very nice environmental smart sensors. So, for example, uh, for water or industrial monitoring or industrial water monitoring, we can measure the dissolved ions or heavy metals or redox active pollutants, PFS, and so on in water. So, so it is not just restricted to um, industrial water. I think for home water supplies also, this kind of sensors are very important. And for embedded calibration and IoT reporting, all these things make it smart. So I have divided the sensors in four parts: for water, for biological smart sensors, optical smart sensors, and then the chemical smart sensor. And I have also added for each of them a 2025 example, which focuses a very recent study of what people have been doing. So when we look at the first one, which is the heavy metal, which is the dissolved species sensing element. So this is what they are measuring with the help of voltammetry or amperometry. A very nice three electrode system, and they have made it actually from plastic bottles. And I would suggest you reading this. I have cited this work. It is from Clean Water in 2025, and they have made auto calibration possible. They have also made ML based quantification with the help of feature extraction. And for in terms of connectivity, they have connected it with phones, and cloud reporting also enabled. So how does it look like? The display looks like this. So you can see the current versus voltage response, and you can check, like you can check from which heavy metal is present. So we can take away this statement, like turns electrochemical peaks into an auditable result, which is a concentration plus confidence plus timestamp. So we can have a real time sensing response with, along with standard deviation, or we can say along with confidence or uncertainty and the concentration of that heavy metal that is present in water. So this was one of the very recent studies of electrochemical smart sensor. So now we look at the biological smart sensor. The 2025 study by and this is published in Biosensors and Bioelectronics. And so what they are trying to do is they're trying to measure pathogens. In this case, they are measuring E. coli. So they have this sensor substrate. When it comes in contact with the E. coli, so basically they have a certain substrate which is susceptible to E. coli, and When E. coli comes in contact with that substrate, then there is a frequency shift. So they detect this frequency shift and then convert it into the concentration present, or how much of CFU per ml is present. That is what they are detecting. So they have done amazing work in terms of this automated design of threshold and contamination alarm logic, and they are trying to reduce the cost also. And they have this classification of detected, not detected, and along with the confidence level, which is also very nice. And this positive and negative control checks are also provided. So connectivity is, they are doing immediate alerting as well as some traceable incident logs. So this is actually a very nice way of seeing a frequency shift into, which is in the, it is actually a microwave transducer that they are using. And they also propose that they will be using more E. coli or more pathogen susceptible responders, or we can say the material which is more responsive towards that certain pathogen. They are going to functionalize the substrate with that particular material, so that they can improve the sensing performance. So now we look at the optical smart sensor. So this is also very interesting actually. So they have used optical fiber sensor, so which is very good for remote sensing. So they dip that in a solution of cadmium, and they convert that output power signal from coming from that optical fiber, and then they convert it into that digital response, and then they do all this ML functioning with that. So, and another very interesting thing is that from the microcontroller, that is ESP32 that they are using, they send it to the cloud. So all the results are in the cloud. They do the calibration, they do all the referencing and everything there, and then it also is reachable from the end user. So in terms of quality control, they do the optical power checks and clean or replaceable probes. So this is a nice example of how an optical fiber sensor can be used in an area which is not possible for human interventions, or which is EMI prone, which is electromagnetic interference. So in those hazardous areas or industrial waste areas, I think it is a very nice use case for this kind of an optical fiber sensor. So optical fiber smart sensor. So now last is the chemical smart sensor, which is a chemi-resistive sensor, but they have also implemented the smart element here. It's very interesting that they are using this for gases or VOCs, and for indoor air proxies, as well as in any buildings or plants for continuous monitoring. And the essential part of smart is that they have been able to get automatic drift correction with the help of this ML intervention, I would say. So they first, what they do is they get this data, the sensor data. So if you want to label all the data manually, that is like, I'm talking about huge millions of data points. So it's very difficult to label those data. So what they do is they have some amount of data which is labeled data. Labeled meaning which is good, which is bad, we have that labeled. So with that data, they use some non-labeled data, which is fed into the domain adaptation part. So with the help of a CNN, which is convolutional neural network, they actually convert it into some features. They extract some features from that. They look at the patterns of the data that is happening, and with am kind of trivializing it by using the term pattern recognition, so that I can make myself more understandable. So with the help of that, they extract a feature. Feature meaning, okay, this represents that. And then what they do with the features is they try to see how much they are matching with the other data, with the old data, which is labeled data. And then they, with the help of a distance matrix, they actually classify it and provide weightage to the data, which is a good data. If it is a good data, it gets more weightage to be considered as a trusted data. And if it is a bad data or the distance is more, then they will say that they will classify it as a bad data, and then it will not get enough weightage to be considered as a trusted data. So this is how the smart part works. And I think these are the parts where we need more research for this calibration purpose, how we can use this whole algorithmic part so that we can automatically do this, and we can comply with I mean, we can generate these logs, compliance logs and maintenance scheduling, all these things automatically. Now, the industrial value statement would be smartness is the model adapts to sensor aging using unlabeled field data and reducing recalibration cost while maintaining accuracy. So, why I chose to do that is sensor aging is a huge problem for people. I think those, if anyone is present who is working with sensors, they will agree with me that sensor aging is a huge difficulty, because the shelf life is always a question that we are also asked in our presentations, like what is the sensor drift, what have you done about the drift, what have you done about this recalibration. So all these questions can be answered, I think, if we take these components into consideration, because there are too many things working when we are working, or they're under play when we are working with sensors. So we need this help. So concluding this part, I would say that with the advent of IoT and AI and this utilization of nanomaterials, which is again I'll come back to. I think this has actually revolutionized this sensing phenomena or the sensing domain, not only for water but also for other air pollution and soil pollution, I would say. And it can also offer, if the research goes on in this direction pretty well, then we can expect the sensors to be cost effective. And our goal is to make these sensors more affordable so that people can reach these sensors and also use this in a very easy way. So I would like to see if there are any questions, because now I will move on to I can take a short break for people, like before moving into my work. So if there is any question until this point, I would like to ask. Is it okay, Doshi ma'am?
Yeah,
Okay,
yeah.
there are.
If the audience, they can unmute or they can post in the chat also if they have any questions. They can wait for a couple of minutes if they want. Otherwise, you can continue.
Okay, okay.
Hello. If participant have no questions, ma'am, I
Yeah,
have question
Okay.
regarding edge computing. So can you put some focus on the edge computing? So because that is one of the recent research area.
The edge computing.
Edge computing.
Edge. Okay, okay, okay. Yeah, yeah. I will. Okay, maybe I'll share again. Okay. Mm. Yes. So, do you want me to explain it in terms of a sensor, or um, how it is being done?
In terms of how the processing is done by using edge computing and how it is
Okay.
different from conventional processing.
Okay. Okay. So, by when we are doing conventional processing. Hello? Hello? Yeah,
Yeah,
so,
you're audible.
oh, okay. Okay, so when we are talking about edge computing and not cloud computing, that means the computation is going on the device itself. So we are not sending all the data to the cloud. The data is there within the device, and all the interpretation or AIML intervention, you can say the calibration, is being done on the device. So we need to make sure that the algorithm is not taking too much space, because it is also dependent on the resource of the device itself. So for a handheld device, I think it is very important to make sure that, so that is the edge. So it is important that we are we are using enough, I mean, we are conserving the use of memory or use of the resources within the device. So all the computation, or you can say calibration, is being done on the device. So so why is it good? Is because it's a local thing. So it's happening in the device. So you are not sending out the data to the cloud and then again bringing it back to the cloud, from the cloud to the device. So if you want, let's say, an instant alert, for that you need edge computing. If you want an instant, for example, our watch, smartwatch, it is an edge computing. There, it is an edge computation happening. So where um, all these things are happening on the device. So that is what makes it good, and it conserves the energy. It is more resource efficient. I think that is how I can define right now the edge computation. Did it help?
Y- Yes, ma'am. Thank you. Thank you for explanation.
Okay. Okay. So should I move on to my next part?
Yes, yes, you can.
Okay. Okay. So I have. Okay. So now I would like to connect the previous part with my own research during my PhD. And so this is again a very interdisciplinary part. So I would like to mention before I start that it has some components of electronics, but also some components of material science. So I think it can cater to different audience. So so I worked on heavy metal sensing, and so as we all know, the scenario of heavy metal elements in India is not really good. As you can see in the map, the permissible limits are within ppb range, whereas it's always higher than that. And in Ganges plain also, and in southern India also, we see a lot of lead, nickel, and also which I have not here shown here, but actually there is huge amount of iron, and I mean more than we need, iron and zinc, that are polluting our rivers. So what happens is heavy metals, the sources are industrial waste, then domestic waste, and battery industry, landfill leaches, and mining, which come to the groundwater, and then eventually it meets our food chain, and it accumulates in our body and creates a lot of problem. So for example, lead and mercury can cause joint diseases and ailments of kidneys. Cadmium can cause kidney damage, and chromium can cause lung damage and cancer. And arsenic exposure can also, I mean, long term arsenic exposure can cause skin damage, abdominal pain, blackfoot disease, so on. So I have concentrated my research mostly on lead. And as I had previously mentioned that, so 1 ppb, 10 ppb is the permissible limit for lead, which is not the case. But for chemi-resistive sensor, I will come back to this point that my sensor is in the ppm range that I have worked on. So the inspiration was obtained from the FET technique, which is the field effect transistor technique for heavy metal sensing or any contaminant sensing, which was the starting point for my research. So in an FET based device, you have a source and drain and gate, but mainly you have the channel between source and drain, right? And you have a material which comes in contact with the analyte. And when it comes in contact with the analyte, the current or the voltage, whichever is the measuring that you are measuring, will change. So what happens basically in this case, I have explained with mercury ions. So when it is connected to the power and you have a graphene sheet, which is our measuring um, material, so when it comes in contact with that, then there is an exchange of holes, and holes will increase in case of a p-type material based on what you have put in the what you have functionalized the graphene sheet with. It will increase the conductivity when it gives out, when the Ag or the mercury ions will give you the holes. So then it increases the conductivity of the channel between source and drain, and that change in the conductivity is measured with the help of the FET device. So I have tried to reduce this concept into a chemi-resistor. Chemi-resistor is a very basic concept for gas sensing, but not for water-based contaminants. Not many studies are there, and we need extensive changes or extensive mm, material modification for the sensing material between the electrodes, but I gave it a try anyway. So we have two electrodes, and the sensing material is in between two electrodes, and they are connected through the supply battery, which is a 5 volt that I have worked with. And now the sensing material comes in contact with the analyte and it changes the current, and that is what I measure. So we used graphene based material for making this conducting channel between the two electrodes that came in contact with the analyte. So I had a comparative study between a comparative study between electrochemical and resistive technique before starting this work. For example, electrochemical technique requires 3 electrodes, so it is a complicated architecture, right? And when we are talking about a portable device, then a complicated structure like an electrochemical sensor within water for water sensing is a bit difficult. And for that reason, I chose a chemi-resistive technique over electrochemical technique, but it comes with some baggages. So for example, though it is easy architecture as compared to electrochemical technique, but there are some problems like there will be a lot of interference and interfering. I mean, for the interference, I think a more complicated design would help us in the long run. And for electrochemical technique, we check the anodic current change to understand the concentration of the heavy metal ions in a solution. But in case of chemi-resistive, we are only checking the resistivity change, which is in turn actually the change in the current that is happening, and that gives in turn a resistivity change that we are sensing. And it's a complicated design, and for electrochemical technique we need an external circuitry also, for which we also need for a chemi-resistive technique, but it's rather easy for a chemi-resistive technique as compared to the 3 electrode system. And for reversible change of the sensing platform without the washing, which is a good thing, I was saying that chemi-resistive techniques sometimes is not very advantageous. This is one of the reasons why it is not advantageous, is that it will, the heavy metals which we are adding onto the sensor substrate will stay absorbed on the sensing platform without washing. So you need to take the film out and wash it in case you want to reuse it. So the reusable part is more in case of electrochemical techniques, because we can do reversible changes with the help of our sensing device. I mean, with the help of proper voltage application, but that is not the case for chemi-resistive technique. So again, I would reiterate that this is a 3-electrode system, but chemi-resistive is a 2-electrode system. And for electrochemical technique, it is again, it is difficult to incorporate in a portable device, whereas it's very easy for a chemi-resistive technique. Now, why I chose graphene-based material is because it has excellent electronic property, and the surface area is also good. Because for any nano material, it is very good for sensors, because the specific surface area of nanomaterial is way higher than the regular material. And also it is highly, especially for graphene or graphene based material, they have their room temperature stability is good, and their room temperature mobility is also excellent, which is good for a conductivity based sensor. And as I already mentioned, that the surface area is very high, so the absorption capacity of that material also is very high. And as a result, it gives us this very good sensing properties. So now, this is my basic 2-probe method setup that I made with a source meter and the probe holders. So I will come to the sensor fabrication part, which is a very simple way of doing that. But before that, this is the measurement setup that I did. So this source meter gave me the resistivity change, which is the resistance change, and then I calculated the resistivity from the resistance. And for my setup, I examined that the contact resistance and the spreading resistance were negligible for the material that we were using. Another very good point for using graphene. And for that reason, I chose to neglect these two parts and only take the main part, which is the main, the remaining part of the R total. So now many people also questioned me that why didn't you go for 4 probe, because 4 probe is seen to be more prone to smaller changes, so you can check with even very small changes. Again, I think for a portable device, lowered the number of probes better for integration with a circuit, which is again inside the portable device. And I also realized that for the area of sensor, for the area of the sensing film, I I investigated that 4 probe and 2 probe methods are not giving much changes in the values of resistivity. And for that reason, I decided to go with 2 probe method. And these are some images of how I did it. And this is a microscope with the help of which I can see where I am putting the probe, whether the probe is in contact with the sensing material or not. And this is how the source meter displayed. So you can see that my current is 0.99. So I used to apply 1 microampere, which is again a very small amount of current, and that gave me the amount of resistance. So again, with this very small amount of current, we are not disturbing the graphene material or the graphene substrate too much, because we have to keep in mind that we cannot destroy the sensing material when we are doing the sensing. So this is another very important point for designing sensors. Now, I will come to shortly the response study of RGO, that is reduced graphene oxide, that I made. So as here, the film that you can see, this is an RGO film. So RGO stands for reduced graphene oxide, so which is a derivative of graphene oxide. So we get from very small graphite flakes, we get the graphene oxide, and then we reduce it into reduced graphene oxide, and then we use it for our sensing. So I'm not going too much detail into how I fabricated, how I made the graphene oxide, but I'll come back to it. Before that, I would like to talk about the response of RGO. So this is my very base material, reduced graphene oxide, okay? And I'm using different concentrations of lead nitrate in ppm range. So why I decided to go with ppm range is because in ppb range, I was getting all the response for all my materials below 10%. Just like regular water, DI water. So that's why I decided not to do PPB range, because I need some further modifications or the use of recalibration with the help of some ML techniques to reach my PPB goal with this existing sensor, or I have to design a different sensor. Now, coming back to the present RGO material, where I used ppm level concentration of lead nitrate from 10 to 40 ppm, I saw that there was some linear change, linear relationship between the percentage response and the concentration of lead nitrate. But at the same time, I saw that the response is very low. It's just 40, it's just 10 to 15%. And for this image, you can see that for 50 ppm of lead nitrate also, the for 30 minutes, I waited for 30 minutes for the response, and it was not above 10%. So, and I have also shown with standard deviation for 30 minutes. So this is the case of the base material RGO. So that gave me an idea that, okay, even for 50 ppm, which is a pretty high concentration of lead, it is not giving me more than 10% of response. So I need to do something. I need to change change the material of sensing, because otherwise I will not get a better response towards this analyte, which is lead in water. So these are all lab studies that I'm showing right now. And now I also wanted to show you this small IV characteristics of the base material before I go to the modification of the material. Is that you can see the IV characteristics, it's not changing after 30 minutes also. It's just overlapping with one another almost. And as you can see that when I tried to see how the sensing material works with different pH, when I'm changing it from pH 2 to pH 10 with the help of mixing a zero point 0.1 molar HCl or zero point 0.1 molar sodium hydroxide solutions, it's not good. It's showing huge standard deviations. It's going beyond any kind of acceptable limit, and we cannot do this. So we cannot do regular DI water. We cannot do it with even pH changed water. So now I had to move to some other things. And to add to this, I also did the selectivity study, because when we see that, okay, our main analyte is lead and lead is mixed with some other metal, how does our sensor react? Because in our industrial water or in any water, to be honest, it's not like it comes alone. It comes with a lot of other analytes, a lot of other in the whole matrix, there are many other things present. So we have to design our sensor in such a way that it is very responsive to that one single analyte. If you are going for that single analyte, in my case, lead. So I saw that, okay, for this mixture of ions also, it is not performing well. It is even for 500 ppm of analyte, which is lead and cadmium, I wanted to see. Though for lead, it provided more response, but it did not provide any response for the mixture of ions. It was showing more or less similar response to the singular one analyte. So now, before I moved on to the modification, I also checked with some real water sample, because as I already mentioned, that for drinking water or for tap water, there are so many other things present. So we have to make sure that at least it is within an acceptable limit, or we can explain why our sensor is behaving in that way for drinking water or tap water, or even with the help of Pranav sir, actually, I also tested the water from Powai Lake. So this is very important that you check your sensor with with real life or real water samples also. So all resulting solution concentration were maintained at 50 ppm, and then we checked the other responses as well. So these are all within around like 20%, which is closer to 20% response. So as a summary of this part, I would say that I started with graphene oxide on a clean glass cover slip, and I air dried it and then reduced it to make RGO film, or reduced graphene oxide film. Then I deposited the electrodes, silver electrodes, and then I also showed you the measurement setup where I connect to the probe station, and then I get the resistivity change. So this is the initial part of my work that I did, and then comes the modification part. So here comes the next material that I used for this for functionalizing my graphene is beta cyclodextrin. So there are some studies. If you are interested, I would recommend you go through these studies, because there are very few studies actually before 2018 or something that used beta cyclodextrin for and also for this kind of electrochemical sensing of heavy metals. So though basically there are also some studies that showed that beta cyclodextrin can capture cadmium or lead based on the internal radius of the cavity, but for sensing purpose, this was quite new back in 2018-19 or during that time. So I would just slightly talk about the chemistry and then move to the response. So this is the how the cavity looks like. And when the lead comes and it knocks out these two H and comes and interacts with the O. And that's how it binds inside the cavity of beta cyclodextrin. So this is for one glucopyranose unit, and this is how it interacts with one glucopyranose unit, and that's how it gets stuck within the cavity. And that is what my hypothesis is, that that is what is happening in case of my beta cyclodextrin modified or functionalized reduced graphene oxide. So I also saw, I did not include this, but there were some uh, comparative studies as well, where they showed why alpha cyclodextrin is good for cadmium, whereas beta cyclodextrin is good for lead. So these are all for selectivity studies, because when I'm doing this work, I have in my mind lead. So I have to make this sensor really responsive and selective towards lead. So that's my mind. So this is how I modified my RGO film with beta cyclodextrin. And I'm not going into detail because it's not, it's mostly material science thing. And excuse me. So the final product, I will term it as RGO BCD. So initially I was saying RGO, which is reduced graphene oxide. And now I am using RGO BCD, which is beta cyclodextrin functionalized RGO. So now this is the basic step. So again, graphene oxide, it gets reduced into reduced graphene oxide, then it gets functionalized into beta cyclodextrin RGOBCD, and then lead comes, and this is how I imagine that this is how it looks like maybe when the lead is captured inside the cavity. So now I will jump to the systematic study of the response of the final material. So actually I used different concentrations of BCD, and I saw that for RGO BCD 100:1, with this ratio, our material performed the best. So that's why I am showing the result for only this ratio. So I saw that for this one, though the lower concentrations at 10 ppm or 20 ppm, it was below like 20%. But when I'm increasing the concentration like 40 ppm or 50 ppm, then I get almost 80% of percentage response. So by percentage response, what I mean is the percentage change in resistivity. So the response towards 50 ppm of lead nitrate was more than 60%, which was a lot of change, or lot increase as compared to the regular RGO. And we also checked the standard deviation for 3 iterations, and we found out that as we are going ahead with the time, then the standard deviation is also reducing. Now, if we look at the response study of RGO-BCD, so this is how I calculated the linear part, or what should be the linear coefficient of these functions that will define the response. So this is very important in the next stage, where I would like to carry forward that study of calibration and recalibration. So this kind of data will be very important for those designs. So as you can see that for 50 ppm lead nitrate, the IV characteristics show that there is a change in between 1 minute and 20 minutes. So the current is higher. So that means, the current is higher. That means the resistivity has been reduced for this case. The current is lower. The 10 is the base current, and then with time, the current is reducing. That means the resistivity is increasing. And with this response also, you can see that with pH, though the standard deviation is extremely high in our case, but it follows a certain trajectory where it is starting with 20% and then goes to 40%. So the standard deviation was again calculated with 3 iterations, and this is one of the biggest, I would say, problem or drawback of this sensor. And that's why I think that we need some auxiliary sensors for making these changes. As I mentioned earlier in the earlier slides, that pH sensor, humidity sensors, and this auxiliary sensors will help calibrate our sensor better. That's why I think my sensor was extremely responsive towards the high pH, but with this high standard deviation, I cannot completely say that I can trust this. That's why I need more data and more auxiliary sensors so that I can recalibrate my sensor. So this is a very good use case, I would say. And interestingly, when I measured other heavy metals individually, then also lead was showing higher response, and the mixture of lead and cadmium, all of them with 50 ppm were showing where there is a lot of cadmium. So you can say that cobalt plus PB, I used 4:1 ratio, but it was not showing more than 20%, which is the advisable or which is the acceptable way of taking it, only except for chromium. Chromium showed a lot high response when lead is 10, lead is present only 10 ppm, let's say, and 40 ppm is chromium. So it showed a very high response, which is not desirable. But for all the other heavy metals, it did not show a lot of interference, which is one good part with cobalt, cadmium, and iron. So I can say that the kind of modification that I made into RGO, that was good for good for cobalt, cadmium, and ferrous, but it was not good for chromium. So now I would like to move on to the real world water samples. So again, the saline water was a bit high, but for milky water and tap water, it was more or less what is desired. So it increased above 100% in different matrices. For example, as you can see with saline water, again, I faced this problem. So again, there is the requirement of the smart element here, you see. So that's what I meant by saying that when it comes to real water samples, there are so many things, so many components in the matrix that you need this spatial agents or special auxiliary parts within that sensor or within the entire sensing device. So, summarizing my work until now, I can say that this electrode, which is very simply modified with beta cyclodextrin, it's far simpler than the electrochemical modification, and that's why I used chemiresistive sensing. And here we do not need the supporting electrolytes, and it is a simplification of another three electrode system, which is the FED type sensor, and it is very easy to interfere with an external circuitry. I will come to that point now. But before that, so this is how the comparative data looked like when I look at RGO and RGO BCD, and also the concentration of lead with an actual data, and the linear fit has also been shown, because this is a linear fit, that is how it looks like, but with more data we will have more functions to take into consideration. So now the kind of prototyping that I did, those were extremely lab based. So we produced this 3D printed housing. So I went through three iterations. The first one, as you can see, is the very basic one, where I used this I'll show with a pointer. So these were to support the two electrodes, and the three holes were there. One hole was for analyte addition, and the two other holes were for connecting the two probes. As so, the second prototype was a slight modification of this one, and you can see that it is taking way too long for good response, or the peak response, you can say. And this was the second iteration where result of this one, where the whole assembly looked like this. I had an OLED um, display, where so the good thing about this design was that this housing could move on this substrate, so we could do multiple measurements on a single film. So it's not like just after one measurement I had to change the whole film. And the third iteration, where I took the whole assembly, so in the previous one also I connected it with the Arduino, but the Arduino was inside this black box. And here the whole Arduino and the sensor assembly was inside this white box, and a slight part of the sensing substrate can be seen from this hole. And this is how my sensor is connected to the external circuitry. It just needs 5 volt. But again, for the Arduino, I needed an external supply, and also the result was being connected to, or the log we could see on the laptop. And if you are interested, this is the 3D printed housing design, which has a bottom tray and the space for placing the circuitry. And this is how the top tray looked like. So this much I did for my prototyping in a lab based. So now my question to myself, and now that I look back at my PhD work, I look back like, okay, so my when we are talking about finding out the correct material which is enough responsive for the certain analyte that you have picked, so it requires knowledge and and also a lot of trial and error with the material itself, because you need to characterize it thoroughly, you need to understand what is happening, the science behind this. So I think with, as we are living today in the world of AI and ML and everything, so I think it is a little bit easier for us to do all the things, because once you have got a good sensor, then you start thinking about, okay, now we make it a lab prototype, and then we convert it into a portable sensor. So these are the stages you go through. So I know there is a lot of work to be done if I want to make it a market ready portable sensor, and which can be deployed anywhere. And so I decided to look back and find out some gaps. Like, what are the gaps in my own sensor in order to make it a smart portable product? So I think for researchers also, and for teachers also, it is very important for us to keep on finding out if there is something new that we can do in our work, or we can improve our work. So that's what I try to do today, actually. That, okay, so what are the gaps? We can say that, well, we only did 10 to 50 ppm. So though we tried with other concentrations also, it did not go to the ppb level. So for industrial level, even if it is okay, but for some home water supplies, we would want the level to be below ppb. So I could have also included an alert component where it would say below ppb or after, below 10 ppb or above 10 ppb. That could also be done. So this is one of the points that remained a challenge for for my sensor, where I did not end up doing the correct calibration for the ppb level. So it requires more research and more data. And when it comes to a portable product, or when we talk about, so our time, we don't have time, no one has time nowadays, so they want instant result, instant alert. So for that, this sensor is not going to work, because it takes 30 minutes to give you a stable response. So we need to make sure that, okay, we calibrate the sensor in such a way, we take the very first like 5 minutes or the very first data point, and we calibrate with that data. But I waited for my own sensor, I waited for it to stabilize, because it was a lab based sensor first. So I waited for 30 minutes and I stabilized the result, checked the standard deviation for 3 results, and then reported the results. So we need these kind of data, but then we can utilize it to make it smarter with the help of better calibration. Then the manual sampling. This is another part which is, maybe this is again for a portable sensor also, the manual sampling is still better. But the other problems, like the manual sensor producing, or the sensor make preparation, that is actually a point of problem, because there are problems of reproducibility. So I also tried some laser implemented routes also, but thankfully, my way actually worked very good because I attained very good resistivity for and very constant, stable resistivity for my sensor. So I went along with that. So, but I would like to make some changes and reduce the manual part and increase the machine part in terms of, fabrication of the sensor so that not only for reproducibility part, but also for batch production, because that is what you need for an industry level smart sensor. And the prototype that I made was a 3D printed housing, but also this is not, I mean, for a scalable sensor, we have to think about more options, right? And also for a portable situation, we need a circuitry that can work uh, uh, without a constant external battery. It has to work with an in-house battery. I think that problem can also be solved. That's not the biggest problem, but we also need these problems to be solved, like the drift handling. Why drift handling? Because with time, the sensor ages. So if it is showing 40%, I'm not sure that it is going to show 40% after 1 month. It can change because of humidity. So again, we need these auxiliary sensors so that we can make sure that, yes, I have this data and I have all the drift data also, and I have calibrated and classified my data accordingly. And last but not the least, I would say that for the selectivity, I consider my sensor to be selective to lead, but I have not checked with the whole matrix or all the heavy metals that are present on Earth. I haven't done that, so I am not sure whether it is not selective to zinc, let's say. So, and especially with the saline water problem, this is another issue which caused serious trouble for the selectivity domain. So, keeping all these things in mind, I think there is a lot of work that even for a simple sensor like chemi-resistive sensor, we can do and make it smarter. So, now I am almost towards the end, and I would like to conclude by mentioning some advantages and not disadvantages, some challenges of this kind of sensors. So the advantages are definitely you get immediate alerts, pollution events can be easily sent to you, the alerts can be sent to you. So real-time monitoring is the biggest green flag, I would say, in today's language. And I would say the portability and cost. It is our duty to make it cost effective and also energy efficient. And especially, it is highly selective for a certain pollutant or a certain contaminant, even for low concentration. So these are the advantages that we need to look for when we are designing a smart sensor. And when we look at the challenges, definitely the stability, the drift problem, and the biological component not sustaining themselves in harsh environments. These are biggest problems. And the interference, as I myself um, had the huge face off with. And I think for complex matrices, we need more sensors and more data so that we can do the computation properly. So with this, as we see that every day we are seeing one or two new models or some new iterations of the models. So with the help of that, we have to check how we can use it for our own benefit and for a broader deployment and development of more robust and self-calibrated system. So that would be the future. So I would like to thank Professor Dr. Parkale and Professor Dr. Doshi for giving me this opportunity, and also Pranav sir for recommending me. And I started this work under his supervision, and also for my other works at IIT Bombay. And I would definitely like to express my gratitude towards my supervisors, Professor Shukla and Professor Bandyopadhyay and Professor Saxena. So I would also like to say that I have used these tools for some um, diagrams and for the icons. So recommend it. And thank you so much. So
Yeah. You were exactly
on
10
time.
minutes before in time you completed. That's great.
Hello.
Can I request the audience? Yes, sir.
Now we will take a question and answer session.
Yes.
Okay. Should I? Okay.
Participants are requested to raise the questions, or you can put the question in chat box.
Okay. Is there any?
I will just unmute. Okay. Participant can unmute themselves. Madhuram, you have unmuted actually from our side. Just unmute yourself. Okay.
No.
Good evening, ma'am.
I
Hello, sir. You are not audible.
Hello, am I
Your voice
audible?
is echoing. Yeah.
Now I am audible, ma'am. Good
yes,
evening to all.
yes.
I have a question, ma'am. In the field of image processing area, so we are using the image sensors.
Okay.
So the noises also comes under the image processing areas also. So how can we check out and easily detect the noises in the image processing areas where the image sensors are used in that field?
Okay. So, though image processing is not my area of expertise, but what I'm trying to understand is, are you using any AI ML technique for the image processing, or
Actually, ma'am, we
how
are
do you?
using the image sensors in the digital image processing system.
Okay.
Image sensors we are using.
Okay. And then you're trying to classify which image is what,
Yes,
right?
yes, yes, yes.
Okay. So you're talking about noise problem that you want to change. You want
Yes, ma'am.
to reduce, right?
Yeah.
So what kind of classifiers do you use? Can you tell me? Because in my current research, where people work with this classifiers, or so what I can say is you have to
You are
start
just
with creating a gold
ma'am
data
telling the
set.
four categories of the sensors field. You are categorized into the four categories in the starting of the session.
Mhm, mhm. But these are
So,
all environmental sensors.
yes, yes, yes. So image sensor is categorized in which category?
Image that is not going to fall into any of these, unfortunately.
Okay. Okay,
This is
ma'am.
a
Okay,
completely I would say a data science problem.
okay, madam. Okay.
So
Thank
Can I answer, madam, to this question?
yes, please.
Okay. So actually, image sensors are what? Certain acquisition systems. Okay.
Yes.
And then you have to scan them. Then they might be anything like ultraviolet scanners also are there. Your CT scans also are there. Digital X-rays also are there, and your camera. is also a scanning or acquisition system. Only these systems can understand that it is an image. And then we have AI algorithms for classification.
Yes.
So sensor, it does not like, there is motion sensor which can sense that motion and then do, but there is no sensor like image sensor. It is a image acquisition system.
Mm-hmm.
That is what I have, like, my expertise lies in AI/ML and depending upon the digital image processing and all. So this is what we have done till now.
So, what kind of, if I may ask, like, what is the pipeline for or the framework for your um, disambiguation, let's say? Like, um, how do you differentiate? So, which classifier do you use?
Yes, now depending upon what is your problem statement and which algorithms you are going to use, there are number of classifications. So what type of a data you are having, whether it is a supervised data or a unsupervised data, again classifications are different, and that depends totally on the image and the method by which image is acquired. And in the
Okay.
camera or the acquisition system, sensors are there. So that senses the intensity, luminance, and all those things.
Mm-hmm. Okay. It's an
Okay,
intent.
thank you, ma'am,
Okay.
uh,
Thank you.
for the answer. Uh, any more questions?
I hope the doubt is cleared for the other person who had this question.
Or else then you can communicate one to one and resolve the issue, I feel.
Okay, then no issue.
Thank you, ma'am.
Thank you.
Hello.
In the chat, yeah, I'm not seeing any questions. Okay, so shall we call this as the day? Okay, because
Yes.
the other, yeah, the next speaker is already joined.
Oh, okay.
Okay. So it was really
Thank
nice
you.
to have you, ma'am. Madhurima, you said, but
Yes.
then it's okay. Yeah.
Yes,
Uh,
you're very senior to me. Please call me by my name.
no, 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 no. In this, like each one has his own specialty and all, right? So it's
Yes.
better to give his her own expertise in that.
Yeah.
Okay, so we at this end, as an organizing committee, express our sincere gratitude to our esteemed guest of honor, the senior researcher in Berlin, Germany, for gracing today's ATAL's faculty development program. Your distinguished expertise in nanotechnology and sensor technology added immense academic and research value to the session. The talk on the advances in smart technology provided deep insights into cutting edge research and real world applications. The global research perspective inspired participants to think innovatively and align their work with emerging technologies. So, again, on behalf of the organizing committee, we thank you for your invaluable contribution, time, and inspiring interaction with the faculty members. So, thank you once again.
Thank you.
Thank you very much, ma'am.
Thank you so much for having me. Question, but I'll answer on the chat.
Yeah, sure. You can be
Okay.
there. If there are many
Yeah.
questions, you can continue till the next speakers. We
Uh,
can, Parkar sir, for 2 minutes. Can we take a break?
no
Till
problem,
then,
ma'am.
yeah,
Yes,
she
yes.
can
Still,
answer in the chat if she has any questions. And then we immediately will join. Uh, the next
uh,
speaker, I just communicated with him. He's there.
it's
I think he joined.
it's a Dr.
Meanwhile,
Kiran.
hi,
Hi, sir.
hi. Can I test my slides? I mean, meanwhile, you
Yeah, sure.
people can go for a break. Yeah.
Yes, sir. Welcome, sir.
Hi. Yeah. Hi. Thank you. Good evening.
Good evening.
Hello, sir.
Hi.
Yeah, he's
Hi,
testing
Mr.
his
Yoder.
slides. You can share the slides and just check.
Yeah, so let me.
So in between, if any participants have any question, any doubt, you can ask in the chat. Madhurima is still there. She can answer.
Can you see my screen?
Yes, sir. It's
Yes,
visible.
yes.
Visible,
All
sir.
good. Your audio,
Uh,
it's audible, and yes. Dr. Madhurima, you have one question. How to decide to use electrochemical technique and
Yes,
chemi-resistive technique for testing?
yes. So I was about to say that if it is in my experience, I mean, with chemi-resistive technique, after using it, I would say that it has some problems that can be, I think, resolved with the help of three electrode system. But now the three electrode systems are also being very well fabricated on PCBs and on I mean, on these substrates. So I think in today's world, it would be more relevant if you go with the three electrode system because it is more responsive. I think, and we can think about the circuit connections and everything later. But first, we have to make sure that the sensor works really well. And for that, it is advisable that the electrochemical technique and also think about fabricating a handheld portable sensor and in what way we can fabricate a three electrode system. I mean, if I get an opportunity to work on this field again, then I'll go with that. So I think look into that more. Thank you for the question. I would like to thank all the attendees for their attention, and I'll go now.
Yeah. Okay, thank you.
Okay, thank you.
Bye.
So now we are here back again within 2 minutes to again eagerly waiting for the speaker to speak. I would like to start with his introduction. Dr. Prem Sai is currently working as a staff engineer to device design at IVP Semiconductors, focusing on innovation in power semiconductor device design. Previously, as a senior project engineer at SemiX, that is Center for Semiconductor Technologies, he contributed significantly to semiconductor workforce development, leveraging hands-on expertise in fabrication processes, process integration, electrical characterization, and TCAD simulations. He gained through extensive work at IIT Bombay's nano fabrication facility, that is IITB NF. During his PhD, he was selected under the Indian Nanoelectronics User Program, where he received specialized training and mentored PhD students across domains, including MOSFETs, GaN, HEMTs, then NVMs, MEMS, and microfluidics. Contributing to INUP Phase 2 and Phase 3, his doctoral research focused on low temperature alumini dielectrics for graphene fit on both grades, silicon and flexible Captain's substrates, leading to publications in IEEE, TED, and microelectronics and solid state electronics, that is MSSSP. He holds a master's degree in VLSI design from SSN College of Engineering, where his work involved TCAD based studies in FinFET for RF applications and radiation effects in SRAM architecture. Dr. Premzai is passionate about bridging device physics, fabrication technology, and practical applications, and actively engages in faculty and student training through concept driven and hands on learning approaches. So, here we are, sir, without taking more time of you and handing over you to the platform. We are really fortunate and thank you for accepting our invitation. And the stage is yours, sir.
Oh, sorry. Yeah, thank you for the warm welcome. I hope you can hear me.
Yes, 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 all good.
Yeah, so we just want to. Yeah. So can you see the slides changing also?
Yes, sir.
Okay, thanks. I good evening. I know this is your sleeping time, but I'll make sure that I will not bore you guys. So yeah. So the topic they have given it to me is introduction to semiconductor fabrication and clean room technology. So this is little of the topic from what you have studied. I went through the schedule and I saw there are some talks on FPGAs and nanoelectronics, all that. So, but uh, I think last talk also they showed the sensors, but I didn't see, I didn't listen fully whether did they show any fabrication, all that. So I think I'll introduce to kind of tour to the tools, so that I mean I won't get into a lot of modeling like device modeling, process modeling, all that. So I'll just uh, make sure that you won't get bored. Okay, so yeah, so before getting into the topic, so this is where I work now. So we are a fabless company, means we do only design and development. Okay, and we send designs to Taiwan and all. So this is where we discrete, they call discrete devices, so packaged you are seeing here. And then after that the circuit team, system team, they kind of integrate this modules. So mostly these are high power modules, so which can be used in electric vehicles, all that. And even inside the vehicle also we need to communicate between the modules. So for that there is this RF module like Bluetooth, Wi-Fi, all that. Okay, and if you see, these are converters like AC to DC, DC to DC, all that you needed in electric vehicles. So that is what we make. So now get into the outline. So in the outline, first I thought I'll start with chip war. I don't know whether people have covered it. So I thought I'll start with little geopolitical scenario. Then I will just show the design flow, what you guys have already seen till now. Then I'll show different ways how to improve the performance. I'll just introduce. So, and yeah, so then what is the state of art devices in using silicon technology and all. Then the semiconductor manufacturing process flow I'll show. Then what is front end of line and why it is evolving, all that. So I'll just flash few slides on that before going to processes. Then I think MOSFET scaling, a lot of people will be knowing, but I'll just show the Intel's roadmap. Yeah, then we will be seeing, just a second. Then we will be I will be showing the unit processes. In that, I'll just show how wafers are made. Then the lithography, which is a key if you want to plan some project in future. So these are the key steps. There are so many unit processes in the process line, especially in the manufacturing industry, semiconductor manufacturing industry. But on the academic level, these are sufficient, I feel. So that's why I kept. Then apart from that, I was told to talk about some clean room technology. So I'll be showing what exactly is the clean room. So what are these particles and all. So nowadays we are seeing pollution, and a lot of construction sites, they are keeping one monitor, like uh, how much is my PM 2.5 and all. So 2.5 micrograms per centimeter cube, all that. Those are also particulate air. So how they are filtered, all that. So those things I'll just show here. Yeah, so this. So why the chip war, why India is currently investing in semiconductors. So yeah, so as we all know, there is this trade war between China and USA happened. So they are keeping restrictions on Taiwan, not to give their you know advanced technologies to China, and so that has been properly documented in this one book called by Chip War by Chris Miller. So because of this geopolitical tug of war between these countries, so as in India we have opportunity. Okay, so what is the opportunity? So the government of India, by seeing this, they have launched the Indian Semiconductor Mission. Okay, so the objectives of this is we have to become self-reliant. Then for that, and we need to improve the supply chains also, because as a India, by heart people are really good at heart. I feel like so. I mean, then yeah, I'm digressing. So then part of this Indian Semiconductor Mission, lot of companies like Tata, they invested. The first Indian government also invested a few $1 billion. Then followed by in 2023 recently Tata also invested. So they are coming up with new fabrication and manufacturing unit in Dholera, Gujarat. So they're working on it. And Micron also in Sanand, it's already set the packaging and all. So then in Assam also, Tata is planning to keep one packaging facility, or they call it as a OSAT, after the chip is fabricated, in order to convert that into, the packaged chip, like, on the, like a module. So all that. Then there is something, one more company called Crompton Greaves and all. So, but as in India, we are highly populated, but on the other hand, we have very less skilled people, which are needed for the country in order to drive this, semiconductor mission. So what I feel is, as a part of this workforce development, so we need very skilled semiconductor engineers. So that's why we need to understand this geopolitical scenario. That's why we are, I think, part of that. We are seeing this program, the faculty development program. Okay, yeah. Just a second. So yeah, you might have seen this. I don't know. I think a lot of people might have shown this VLSI design flow. Like what normally people do is first, let's say I want to design some ALU or some full adder, half adder, let's say some digital system. So first we need to specify the system, then we need to write code in Verilog VHDL to check the functional. So sorry. So to check the functionalities. So then there is a circuit design. People do, how to add this, blocks. Then there is a, after making the blocks, we need to physically arrange them. Okay, so that is called, after this physical design only, it will go to fab. So that people call it as a tape out, but in physical design, you have to do all this. This is like how we construct the house, the same way where we have to keep the hall, bedrooms, all that. In the same way, different functionality units, you have to arrange. That will come. So here we will be just checking the functionality, all that, right? So here we physically arrange. Here we do just a feasibility check, whether this particular function is feasible or not. Then there is this, then after all this is done, the tape out can be sent to fab and then later packaging and testing. So this is where, semiconductor process technology is a mandatory. So when fab and packaging, both people need this, insight on the unit processes, okay, or process technology. So the other, other thing I want to point out. So let's say we want to design a system. like how we can improve the performance. So there are different solutions. Like, as a device engineer, I can do, I can, come up with new design. Like, now we are going through MOSFET. Then after that, there is a FinFET, that gate all around, all that. So then we play with the geometry, all that. So that is one way. The other thing is circuit. So they circuit people, we assume, okay, foundry people have given us the information in the form of a PDK. So we just try to arrange them and check how is my functionality, and they check the latency, and static time, static STA analysis, all that. So that we will do. And process, this is where people play with the processes. This is like it is exactly like cooking. So how you will what is the process, like after making atta or a dough, how to convert that into a good maybe bread or something. So in the similar way, so what are the ingredients needed for making particular recipe, to make a good dish and all that way. Similarly, the other one is packaging. Now the chips came out of process technology. How you will arrange, whether you arrange side by side or you do 3D integration, you stack them. Like nowadays, you have seen Micron. They sell the memory chips, like flash memory, okay, NAND flash, all that. So they kind of arrange them, in a 3D manner. So like around 232 layers of the, for the NAND, for realizing the NAND functionality. And so that's how the 3D chips are built. So similar way, if you see NVIDIA, what they do is they take chips from here and they stack them to get the high bandwidth. Nowadays, we need high bandwidth, right? So we want it to be faster, all that. So they just place. The other thing is system design. Like, okay, I mean, they just take all this and they'll arrange and see. Okay, these are other ways, people for same problem statement, you can approach from different I would say disciplines. So different disciplines can be added. So sometimes even the interdisciplinary people also have to work. In industry, there is something called DTCO, Design Technology Co-Optimization. So they kind of work both, with the design team, device design team, and process team, and they kind of optimize similar way. So they can go in tandem also. Okay, so these are all the approaches we can try to improve the system. But in this topic, in this lecture, we are going to focus on this process technology. That's what I meant here. Now this you have seen. So this is how the capped processor. Okay, so then if you decap it, what you see is a bunch of blocks with different functionalities. They are kind of etched or fabricated, we can say. So, and they are at the end, finally, if you see, they're wire bonded. So this will go on to the PCB chip and all. So let's say if you zoom some of the blocks, if you see there is this cache memory and CPU for doing the all the computational stuff can be done, and for accessing the data, so the cache memory and also just showing this as an example. But but what is the building block for this kind of billions and billions of transistors is our MOSFET or metal oxide field effect transistor. It's a P-type and N-type. So P-type is like where you have the P-type substrate, okay, and what you do is you give the potential to invert the channel into N-type. So here also it is same. So you invert the channel where the holes will be flowing from here. So these are like this is a source, this is a drain. So you kind of give access from source to drain by turning on the gate. So I think I'm assuming that you know the basic operation of the MOSFET. Okay. So now let's see, what's happening with the state of art MOSFETs and where and all we have achieved. So in the I just want to show the current scenario, what and all happening with the silicon based FETs. So if you see whatever we were taught in the textbook is planar FET. Then then there is something called FinFET. As we are scaling down, so they don't know whether to push it up or not. So if you see, there is this protrusion out of this place. So where the gate is, it's like the concept behind this is there is one effect in devices called short channel effects. As we are scaling down the channel a lot, so the gate cannot control the channel. So I mean, so in principle, the gate has to give access from source to drain. So there should not be any leakage. Then it is a bad. So let's say if one gate is not sufficient, let's put more gates. So that's the concept behind this, all the development. So if you see, there is a gate wrapped in 3 directions. So left, top, right. So there is a gate. So then there is this gate all around. So here there is a gate around on 4 sides. So let's say, I mean, when I was studying, they used to say one example. At the traffic junction, if one policeman is not sufficient to control the traffic, put more traffic policemen. So, to increase to improve the traffic situation there. Similarly, in order to increase the gate drive, the circuit people call gate drive. So in order to do that, so put more gates around that way. But these are all backed by something called process, people. So they have to come up with, crazy ideas to come up with this kind of processes, gate all around. It's not, that simple. So similarly, now people are working on the complementary FETs and all. So that is one area, on silicon. Apart from, silicon devices, so there are other fields I just want to, show. So there is a carbon nanotube based FETs and 2-dimensional FETs like, graphene, dimethyl chalcogenides, TMDs, like, MOS2, WSC2, tungsten tellurides, all that, they are also there. Then there are spintronic devices where they won't use the charge property of the electron, but they use the spin property of the electron, and they try to, tune that spin with the help of the magnetic field. Okay, and they can be used in the memory. Okay, there are other other research areas which are interconnects. Once the device is made, you need to connect them to the main PCB or package, I would say package. So we have to see. So here you have MOSFET devices, and so as you see, the metal layers are coming up. Okay, and there are other fields in also going on, graphene interconnects, and excuse me. So here, if you see, there is a stacking of memories and accelerators and all. Nowadays, people are NVIDIA. They're all following this kind of integration of different functionalities in the 3D direction. Okay, I just want to show that now. So I mean, now let's zoom into the whole semiconductor manufacturing process flow. So if you see, you have so this whole thing till you solder or till you make bonds to the packaging lead frame. What you can see is this is divided into 3. One is front end of line and back end of line and the packaging. So just in order to zoom this area, so I have added that figure. If you see, this is a MOSFET. So till the gate is made, so you can call that as a front end of line. Means all the processes which will come before that will fall into this front end of line. Then where the gates are interconnected, let's say to have a functionality like a CMOS inverter, or you want to make it as a current mirror or something. So they're all connected in this middle end of line, and there is something called back end of line. Like after that, because they are in all the nanometers, but if you want to put it on the packaged lead frame, So you have to kind of increase the number of metal layers. So if you see here also the same, like copper, there is a dielectric in between, then copper. So as you see, as we go from down to bottom, the width of the copper line, the interconnects we call, because they are increasing. Okay, so then in the end, what we do, we put the solder. So from here you connect to the lead frame of the chip and the packaging. So this is what if you see, they will design. But most of the people will be working here, whatever the scaling stuff, Moore's law stuff. They are now and other people nowadays, they are trying to work in this area, and this is also a very hot topic. So back end of line also, they are trying to integrate some memories such as RRAMs or ferroelectric memories. They are trying to integrate so that they can be used for some other functionalities like fast accessing or some security. So nowadays anyone can make, but what makes the other company different is, even in addition to the software security is something, but it can be hackable. But people are trying to make some security at the chip level itself. So they are trying to introduce some kind of memory stuff in the back end of line, and there they store the program that will be unique for that particular user. So that's how people are working now. So this is so now we will be focusing more on this, why front end of line is driving, like making, taking the substrate, then cleaning it, then doing implantation, then till the making of the metal. So we call it as a front end of line, right? So why we need to drive that, why they're pushing it so hard, even though the Moore's law is delineating from what Gordon Moore has predicted, but still we are pushing. Why? Means, so these are the 4 applications which needs lot of computational power. So I think they might have taught you in digital electronics. Hello, they might have taught you on in digital electronics. So yeah, if you see for data centers, so what most of these applications are really power hungry. So but for that you can't keep the smaller devices, you need to keep on scaling, right? So if you see, there are a few applications I put. So nowadays this is really hot topic, the AI. So previous talk also I was listening some all this machine learning stuff, all this algorithms, supervised, unsupervised, all that. So they kind of need lot of computational power. For that you need to integrate or cram more devices into area. So that's what. And other application what I am seeing nowadays is this self-driving cars. So Tesla has made one processor, their own design, full self-driving processor. So for that also you need this kind of more computation. So you need to put more devices. The other thing is wireless. So this anyway, whichever cell phones we are using nowadays, they mostly have this Snapdragon processor, and data centers, they're still using all the servers, they're using this. So this all are power hungry and all. So you need to find a way to scale it down and use some device engineering or circuit engineering, and make sure that they consume less power, so that we can have more of this applications. So, and this is just a Moore's law. Okay, so as we see the time, every 18 months, the transistor density has to increase. Okay. Then this is just I got from Intel website. So how the evolution of planar MOSFET. You see, 1972, it was around 10 micron, and just the gate length will keep on shrinking and all. So I think after this point, the gate length is not equal to the node. It is, whatever the feature size in that chip, it will be, but it's a marketing trick. So if you see, yeah, the FinFET has been introduced. in 2011. Okay, and now people are currently doing research on this because after while you make this, there are two problems. As a process guy, there are two problems. One is process variability. Let's say you made some, you made some dosa in a pan. So I mean, let's make 10 dosas. So there will be definitely some kind of variation between the uh, uh, the kind of variation from the center to the diameter of the dosa. The similar way, so if you take a entire chip, there will be wafer variations always. Then we do something called different process. So they all will contribute to this variations. So on the device level, how it will impact is threshold voltage, on current, off current, they all will get affected. Okay, so they also we have to keep it. And then other thing is something called reliability. So how reliable my chip, how many years it will work, 10 years, 5 years, or more than that. So they all depends on the processes, what they do. Okay. Then just I try to show what are the unit processes needed at the preliminary level. So, and I try to make some of the processes here, key processes I would say. So this is RCA cleaning, where we have to do bunch of cleaning steps to clean the substrate, because surface is very important. The same way how we do face wash and apply a lot of moisturizers, sunscreen, all that. The similar way, the surface of the device is important, because we should not have any defects on the surface. So if there are defects, then it will lead to the performance of the chip. So performance, like the gigahertz frequency, there is a drop in the frequency, then the leakage, the traps, all that at the device level. So that's why we need to clean the wafer. If you don't clean it, it will have impact on the electrical performance, which will impact on the circuit performance, then on the system. So it's a chain effect or chain process. So then there is something called photolithography. So photolithography is something, you take the help of the light, use mask, and selectively expose on this. Then you do, you can develop. So it is similar like our, camera film. So nowadays we are using digital. During analog time, so we need to have the reels. So once you capture the sunlight, it is it is captured through the lens onto the film. So then we need to develop the film to get the features, or the whatever the picture on the in the what solution, sodium hypochlorite people do. So that's how it's a similar thing. Okay. Then etching is like, it's selectively, let's say if acid or something falls on our skin, it will try to remove. So it's similar. Okay. So etching is a removal of a material. Okay. Then there is this oxidation. So nothing, you take the wafer, silicon wafer, put it in oxygen ambience, and increase the temperature. So the silicon will consume some part of oxygen, and it will grow the oxide. So simple, the name itself suggests that. And metal deposition. So you need metal after for contacts, like as I was showing in the semiconductor process flow, or front end of line, back end of line, there definitely you need the metal. So for that you need some tools which can deposit. So I will just show later in the further slides. Then other thing is called ion implantation. So ion implantation is nothing but it is used for doping. So the intrinsic silicon is useless. You can't do anything unless until you dope the semiconductor, like P type, N type. I'm assuming that you have studied this in fundamentals of electronics. So p-type means you introduce the boron atoms into the silicon. N-type means you introduce the phosphorus or arsenic atoms based on the application into the silicon and make it, more conductive. Okay, so that's the, and okay. For silicon, we use this RCA cleaning. That is, RCA is Radio Corporation of America. Just the company invented the cleaning. So, but we can't use the same process. Let's say there was other, a semiconductor called germanium. In germanium, they use just HCl and Da, whatever that is, one of the steps. For gallium nitride, there is TOS and all. So different substrates needs different cleaning procedures. So, but here I will be focusing on silicon just to get that, because the surface is important, because on the surface only we are going to make the processors or all the chips, on the surface, like just here. So we need to make sure that it is ultra clean. So that's what I want to say. Now, before going into unit processes, I just want to show, from how the wafers are made and what are those, information regarding wafers in the market, all that, and how to identify, for your research, and why I'll just talk here. So these are the silicon wafer ingots, and how these are made means you might have seen in a lot of videos. So nothing, you take the sand, and the sand, then you put it in a kiln, and you kind of add coke. It's a process, metallurgical process. So finally you try to pull it out from that crucible. Okay, then it will lead to this ingot. By using the electro discharge method, you use the wire to slice the wafers, and you get this kind of wafers. This will have a lot of contaminants, all that, like, because in the metallurgical process, there are a lot of impurities getting, they will get added into this. Okay, so basically what I want to say here is, this is what you get out of the reactor. Then you need to cut if you want wafer, like this size. Okay, now how to identify which wafer is what and all. So these are the, so once this is made, they will be cut like this. Okay, here if you try to write some proposal to IIT INUP facility, so you are supposed to mention what kind of wafer, why, because based on the crystalline direction, like here if you see, there is 100, 111 and 110. So basically, why we need 100 means the electron mobility is on the surface. They will be very good in these wafers. So that's why we have to identify before starting our process the primary flat and secondary flat. Okay, and p-type, you have only one primary flat, small secondary flat and all. Okay, then these are 111, 45 degrees to this, it is like this primary flat. So these are all at the wafer. These wafers are at the lab scale, what I used to use even in my research days. But once you go to industry, because industry is all about yield, I want more chips in less time. So they are all about yield, right? Like how many good chips out of total chips, which is printed under the substrate, and they need more, volume, like, per day, how many chips I can, print on this particular silicon. So they will increase the diameter. So this all inches, they're all, diameter of the wafer, 2 inch, 3 inch, 4 inch and all. So here at IITB, these two are available, 2 inch and 4 inch, because the machines what they have bought, they can support only these two. Industry, they are all big clusters, they'll support all this. Okay, so nowadays people are using 12 inch. So they don't have all this, they will have only this kind of notch. Okay, and the marking will be there. And I just want to show, how the, different wafer diameters which evolve with time. So the same information what I was talking. So after 2002, a lot of CMOS, they are stuck with this, because I just want to say for 2-inch, the thickness is around 275 micron. So so then for 4-inch, it is around 500. For 12-inch, it is around 800, like 725 to 800, that range. So the thickness. So you need to hold with tweezer and all. So basically, you need some thickness. But the front end of line, what I was talking, the CMOS, all the chips are fabricated on the surface only. They won't use all the bulk fully, but you need support. Even though the devices are made on the surface, you need the support to handle the wafers without breaking, because these are all crystalline. Crystal means they're properly ordered materials. Once at one place you give force, it will just cut in that direction. So that's why we have to be very careful. Okay, that's why this thickness is also allowed. Now, yeah, I got some fancy diagram from internet. So I just want to show a wafer cleaning that is followed here and all. So before doing going for device fabrication, once the wafer is taken away from sliced or cut from this ingot, it will have so many metallic impurities. Okay, and some native oxides, everything. So if you directly fabricate devices on that, then we will lose the performance, electrical performance. That's why in order to clean that, we have to go through 2-step process. So that is like you call this is RCA1, RCA2. So RCA1 is a base clean, like you have ammonium hydroxide, and this is a oxidizer, which is peroxide, hydrogen peroxide, and water. So you need to mix them in this ratio and dip your wafers. So then it will remove the organic impurities, like the grease, everything which came from the cutting of the wafers, all that it will go. Then after that, you need to remove. So basically, this H2O2 will kind of form oxide also, and all the impurities are collected into the oxides, what I was talking about before. So they all will be removed here. Then later, so this step can only remove the organic impurities. What about this metallic impurities like sodium, potassium, all the metals which will come from the from the cutting, from the ingot cutting? They all can be removed using the acid. So here also same, instead of the base, here we have to use HCl, and this is oxidizer, this is a diluent. So you mix it and you remove the metallic impurities. Then this is where again, so after every process, you have some native oxide. In order to remove that oxide formation, which is all the impurities are gathered into the oxide. In order to remove that, you need to dip it in HF and DI water. So HF is 49% hota hai. Like you will have 49% HF. So you need to dilute them, make into 2% or 4%, to remove that. So we have to be very careful. So this is about cleaning. Now we have a wafer. Like as I was talking about, now you have a wafer. Now I want to do this process, lithography. So you cleaned it. Okay. So this is an industrially approved cleaning process. Okay, RCA cleaning is industrial. Still they follow in industry. The people who don't have a lot of money, since this is a very expensive process, they just go with the piranha cleaning, all that, but they will lose the performance, as I was saying before. So now let's see the critical unit process. Okay, lithography. So as I said, lithography is, you need to create the sample, patterns on the samples by selectively masking few areas. It's like a mask. Okay, so you mask few areas and you allow the light in one direction and you don't allow in another direction. So I mean, it is similar like the carving of Ajanta Ellora. So here, instead of using the chisel and hammer, we kind of use deposition, etching. Okay, this kind of treatments. And so this is the typical mask aligner tool at IIT-BNF. So nothing, it will have, okay, this is a microscope, but the main important thing is the lamp. So you'll have the mercury lamp, which is high pressure mercury lamp, which will allow the, which will give the UV light. So then it is reflected onto the mirror, and through the mirrors, it is focused onto the. So your sample is here, your mask will be here, so it will just expose. So this is the stage. So basically, why you call this our mask colors means you have a mask and you have a wafer. You have a wafer, you have a mask, and you need light to go through this mask and fall onto this. But when we don't just use one level lithography, we have to do multiple levels to make a processor out of it. So you need to align them. So in order to align them, you need this stage to be. That's what here, if you see, there are this, the stage adjusters, screw gauges kind of things. You will be there. So then it will be exposed. The wafer is exposed. So this is just typical, schematic of the mask aligners. Okay, but industry, they go for different tools, that is projection, that I will show later. So here, if you see, this is where we place the wafer, and here we put the mask. Okay, so I will show what is the mask. And so basically, you have a UV lamp. So in order to turn on the UV lamp, you have UV lamps source or lamp source controller, we can call it. So basically, it is similar like choke on your tube light, which will step up and give the energy to the lamp. So basically, the mask controller the lamp controller will kind of give energy to the lamp. Then once the lamp is on, nothing, since it needs to be directed through mirrors and fall onto the. So, and before using that, you need to. So before performing any lithography, you need to spin coat with something called photoresist. So photoresist is something, a organic material, so which is very sensitive to the UV light. So such kind of, I'll just talk about that. And all this mask aligner tools are always kept in yellow room, because those photoresists which we use, they are all sensitive to the light, visible light, and that's why yellow light, it is not sensitive. So that's why we have to use the. So if you see, the background is all yellow, right? So before going for this lithography, what people do, you need to design the mask. So there are softwares like Clevin or K-Layout. So people just design the mask. So it is like drawing the rectangles based on your design. So then what? So on chip level, what you have to do is you have to do something called design rules checker. So the foundry will give you the one file called PDK, process design kit. So they give. So in that you will have all the rules. Let's say, what is the distance between two metal lines? What is the distance between two wells, or P well, N well, all that. So they all will be into that file. But at the lab level, it is simple. Take any CAD software, any CAD software, and you draw the rectangles, and the rectangles can get converted into the design. So how that is done? Using this mask writing machine. So a lot of people use laser writer. So here we use something called laser writer. So laser writer kind of write the design, whatever you have given, onto the mask. Then after that mask is printed, so you take it onto the lithography machine, which I showed before here. So I just want to explain the typical process, how it will be. If you see, there's the film, and you have photoresist, and this is the mask. You see, this greens are mask. It will allow only in these areas. So once the resist, this is the red one is photoresist. So it will kind of weaken. So it is ready to dissolve like that. So if it is a positive photoresist, whatever the exposed areas will kind of get developed and get dissolved into the developer. The right side, the photoresist. So wherever we call negative photoresist, So wherever the light is exposed, so the resist will kind of cross-link together and become very hard. So the people who are working on CMOS, they mostly prefer positive, but there are people who are working on microfluidics or some SU8 based sensors. All this people, microbiology people, they use this SU8. I mean the negative photoresist. Okay, it's all the chemistry of the organic compounds inside. So photoactive compounds they call it. Okay, then. Then I want to explain something called lamp sources. So as I was talking before, so here you can see there is a lamp light source. So the lamp, so based on the feature size, so we have to choose different lamps, and also there is something called the photoresist compatibility. Okay, so these two things are what we use in our labs. G line and 436 nanometer. If you see here, so there is this mercury lamp. This is a spectrum. Okay, this is a spectrum, wavelength spectrum. So as you go from left to right, your wavelength is decreasing 436, 405, 365. Then there is this something called laser. Okay, whose wavelength is 248, 293, 157. So here I have written. Okay, so currently we are using, whatever this FinFET gate all around, all that they are using this technology, extreme ultraviolet technology. Okay, which is 13.5, but this can be used in the current industry. But if you want to write direct writing like prototypes, so nowadays people they want to make quantum sensors, or they want to write this patterns on the qubits. So that time you can use electron beam lithography. So basically the smaller features uses the shorter wavelengths. Like, so if you want to write smaller features like 1 nanometer, 2 nanometer, 3 nanometer. So in industry, if you go for interview, they just ask like, okay, if you go for like a photo lithography engineer, so they just ask, okay, if I want to write 1 nanometer or 2 nanometer, so which technology I have to use and all. So electron beam is the one. So if you like, so there is always limitation why we are going for different lamp sources. Is, let's say, so with this G line and I line, like 436, 350, 365 nanometer, I can go till like the same wavelength, you can see, right? So, but on photoresist, you can go till 500 nanometers with this 500 nanometer width. The line we can write. So I am saying this gap can be written. So based on the light. So if we take EUV, we can write this the distance between these two will be 13.5, like that. Okay, this is what I want to talk. And yeah, as I was talking a lot till now, is this mask. So this is made it in IIT VNF. So if you see, this is a glass. Okay, this is which is very transparent. And so how the masks are manufactured is like, when you order the mask, you will have glass. Then on top of that, there is a chromium coating, and there is a photoresist material. Glass, chromium coating, and photoresist material. So what this writer, electron or laser, you can use laser or electron based on our feature size. Feature size is what is the channel length or all that. Okay, so if you see here, I have written this black lines. This is a chrome. Okay, chrome. So I mean, there are some people who are who want bigger features. They just write with ink also. Okay, but if you want the sharp features inside the lab, means like in the order of microns, you have to go for chrome or ferric oxide coated glasses. So then you kind of etch the chrome or ferric oxide from these areas and making this transparent, and light won't be allowed in these areas. So that is what I meant. Okay. So then when you are performing lithography, people have to keep a few, ticks in mind. So what is the resolution? So any instrument, let's say if someone says, okay, if someone says I want to write this kind of masks using this mask making machine or laser writer or e-beam writer, so you have to ask, okay, what is the smallest feature that can be written? So if you see, so this is one feature, okay, the spacing between. So if you see, this particular thing is called a critical dimension. So that is what people call node, all that. So then the pitch width, there is other term, which is the distance between first to from this end to this end. Okay, so or you can call it as spacing between plus the critical dimension. So that we call. So overlay is, so you have to do so many levels of lithography in order to make a functional MOSFET or a chip and all. So basically for that, the similar masks have to be written multiple, like one or two. So you have to align this mask with the next mask. So let's say this is a level 1 mask. So then another thing is level 2 mask. So you need to align them. So what is the accuracy between them? Like, okay, so how much you can shift, how much tolerance is allowed, all that you call it as a overlay. And throughput, you know this, you might have heard in, so how many wafers I can print in an hour. So the other thing is defect density. So nowadays, you might have heard about something called ASML company. So what they make is they make steppers. Okay, so they have the technology, state-of-art technology to. They don't have mask aligners. They have this something called projection-based systems. Okay, so these are the important things when you are writing masks. Let's say you have some project in your mind, you want to design, some masks, using Clevin software or K layout. So you have to, make sure what is the first area, total area of my chip. So for that, first you have to keep in mind what is my wafer size that they are allowing in that particular research lab. Okay, in that, how many, what is my die size, how many chips or how many dies I can accommodate. So everything we have to keep in mind and design while doing that. So keep all of this all will come from the laser writer or this machine. So how much it can be printed, how much critical dimension this can print, all that. Okay, so then I just want to show the types of lithography systems here, exposure systems. So these two will come under the mask aligner machines, and this has some advantages and disadvantages. I will just talk. So if you see here, so basically you have a UV source and you have a lens. So you want that light to be focused. So this is a mask, this is a photoresist which is coated onto the wafer. Okay, so basically there won't be any gap. So this will come under something called contact printing. So a lot of people who make microfluidic channels, they use this kind of technique. Even some people who are chemistry people, they kind of develop negative photoresist, okay, using bisphenol A, all that stuff. So they kind of make their own systems. So they as I said before, you don't need for bigger features you don't need all this chromium or ferric oxide based masks. You just need ink. Okay, so such kind of people, what they do, they make those negative photoresist and they put their glass on top of that. They will have this the ink printed plastic sheet, and so you will have you will have wafer, you will have masks on which you stick that particular mask printed on the plastic sheet onto the glass plate and just expose. So such kind of people, they use this contact printing because they don't care about the sharpness, or so they just need some channel. So, and it is less expensive. So as okay, and there are more there are no diffraction effects, and cost is also low in this. Okay, so in all this mask aligner systems, the mask is bigger than wafer. So for 2-inch mask, so the mask is 3-inch. For 4-inch, 5-inch. It's like that because that 1-inch is used to hold the mask in the aligner tool. Holding for holding the mask, you need that 1 inch in those aligners. So that's what mask is bigger than wafer. Because so there is other thing called proximity printing. So when you go to IIT, you mostly use this. Okay, so there is this mask, and you have this wafer, and which is coated with the photoresist. Okay, then there is a gap of 100 micron. So you see through the microscope. So the wafer and the mask are brought close around to 60 or 70 while aligning. So then when it is exposed, it will come and close in contact with it, and it will come back. So that is one way. And whatever the other thing which they use in industry is this. Okay, these are called projection lithography or projection printing systems. Okay. Okay, before going this, the proximity printing or proximity lithography systems, so they have this diffraction effects and higher cost also is associated. Compared to this is higher cost. And yeah, then in the projection based systems, you have this lens, which they call so lens is here, but you have mask here. So in all these three, the mask is near to this. Okay, so here if you see light is allowed to the mask, and also mask is placed. So basically you use two lens. So you use this lens to focus. So that's why the defects are very less. You use two lens, and basically let's say you want to write 1 micron feature. So you have to keep this lens in mind and draw based on the magnification. So basically on the mask, if you write 4 micron, it will print as a 1 micron. So that is what people do. And the mask size is also less than the wafer. So this all will call so basically in industry, the name for this kind of system is stepper, they call. So basically it will step and repeat, expose. So that's how they if you see any Intel links I've given in the references, you can see those videos. So they will be printed that way. So then I just had one slide on photoresist. So nothing. So basically photoresist, as I said, wherever the light is exposed. So based on the chemistry, they kind of break the bonds. So in organic chemistry, there are two terms. One is a bond scission, so it cuts scissioning, and one is cross-linking. So for positive photoresist, so they kind of break, or which they call as a scission. Okay, then whichever area is exposed, if you put it in developer, so they will be more soluble. Okay, positive photoresist for better resolution, as I said. Negative photoresist, as I said, So, and this is a resist contrast curve. So when you buy any resist, let's say you purchased a photolithography system, and then you have a clean room, then you want to do some design. So basically you have to buy photoresist. So for every chemical, there is something called MSDS, Material Safety Data Sheet. Okay, everything they will be giving. In addition to that, you will have this information. So in those, you have to see in those, PDFs in those, MSDS sheets. So you'll have this, resist contrast curves. So how much, how much dose I can give, after development, how much. So in order to develop or expose the entire resist, how much dose I could do. So whenever we buy photoresist, we have to do optimization for achieving the good pattern. So this is all I got on lithography. Okay, then let's go for the etching. So I try to categorize into two. One is wet etch, use the acids or base or any solution, and remove the wafer. Remove the material. So I think people have spoken about materials, right? So there are different materials. For that you need different and variety of chemicals, etch. So you call that as selectivity. I will just show what are the okay. So here in wet etch, the etchant is solution. In dry etch, you use plasma. Right? There are four states of matter: solid, liquid, gas, and fourth state is plasma. Plasma, it is nothing. Even in tubelite, also you can create such kind of thing. So in tubelite, also it is filled with like gas, right? So how we can achieve plasma is you take any chamber and you pump it out, like you create vacuum. So basically, let's say the chamber is in the atmospheric pressure 760 millibar, so you pump the gas. So then that's how you create the vacuum, like around 10 power minus 2. So then you introduce the oxygen or argon, any inert gas, and you let's introduce that gas between two electrodes, anode cathode. Just give the potential difference, so it will break, and then you get the plasma. Okay. So what in dry etch people do is you take the ions. So plasma is neutral, but it consists of ions, electrons, okay, neutrals, all that. Okay, what you do, you drive them. So you accelerate them by giving different voltage and go and hit it, on any substrate. So it will create damage and remove. So that's what I meant by sputtering. So basically, the ions which are created in the plasma, they are accelerated towards the substrate, and they will be removing. So other thing what they do is the similar way we send gases. Okay, so if you do this process in the dry etching, you will have highly anisotropic. Means, okay, there are two things. What is isotropic? And isotropic is everywhere it will be. Anisotropic is selectively it will go. Okay, so basically this kind of dry etching is mostly used in industry. So which is highly isotropic and highly selective. Means, let's say I have SiSiO2. I want only SiO2 to be removed. That's what is called selectivity. Okay, so I'll just show. But when it comes to wet etch, you have, like, once you put your wafer, everything will be gone. Like everything is clean. So like RCA cleaning, all that. So that will come under wet etch only. Highly selective. Okay. So we don't want that when we are doing patterning. Like after lithography, we don't want it to happen. So that is the time we have to go for dry etch. Okay. Then I just want to show what is the etching chemistry. So it's nothing. It's just 3 steps. So first, the same 3 steps I have just made in this figure. You have substrate film. Let's say I want to etch this film. What you do, you put it in a etchant solution. So what will happen? They will go and react. Okay, so mass transports of reactants will go and attack this guy. Okay, then there will be reaction. Then some will be consumed, and then there will be byproducts. So that's what these steps. Okay, then I just want to show this diagram. So where what you call the terminology in etching. People, whenever you write proposals or in the you have to ask whether it is completely anisotropic. So anisotropic means you will get like this. Partial isotropic means there is some angle associated, and isotropic means even though you put mask and all, so it will keep etching in all other directions. So you have to keep, and depends. So here, if you see isotropic etching, the same isotropic etching, the same rate in all the directions, whether it is horizontal, vertical, you just put it in, everything will go. Okay. Anisotropic means it depends on the crystalline orientation. So basically, as I introduced in the previous slides, there is 100, 111, 110, all that. So it depends on that orientation. Because, so let's say 111 crystal. So the atoms are so dense, so it won't undergo a reaction easily. So the rate of reaction in the direction will be less. But if you have 100, yes, there is a space between the silicon atoms, because silicon and crystalline terms, it will come under cubic, or there are face-centered cubic, body-centered cubic. Okay, simple cubic structures and all, which will fall in the Bravia lattice, all that. So yeah, that is a different thing you can read if you have time. So basically, anisotropic edge depends on crystalline planes, okay, then orientation of mask. Like if you misalign, it will go in that direction. Then I just want to show here the key ingredients on wet etching. So you have oxidizer once. So basically, the solution I'm talking about, you will have oxidizer, which will have this H2 hydrogen peroxide or some weak acid. Then, so what oxidizer will do? It will oxidize. So let's say you have metal. So then it will form its own oxide if you react with any of this. Then you need to remove that. So that's how you need acid or base. Similar like RCA cleaning. Then you need some water or diluted media or weak acid. So this is what any etchant will have. But when we are buying, we have to make sure that you need to have good selectivity. Let's say I want to remove SiO2. I don't want it to etch silicon. So you have to make sure you have to buy such kind of etching solutions. So then some figure of merits I try to keep. So there are two things which you have to keep in mind. One is selectivity and anisotropy. So selectivity is very simple. You have a substrate, you have let's say film, and you have masking material. Okay. Now what I said, I now I put it in any solution. So if you see here, it is trying to etch only this, right? So the basically it can be formulated into something called vertical this vertical component of the film to the vertical component of the mask. So how much it is etched, because once while performing photolithography, it is said some of the mask material like photoresist can also be affected, but how faster it is difficult. It is different for different photoresist. But normally when we perform etching, we have to create this masking material such as photoresist. So and then when we put it, they also will be etched, but this will be faster than this. So that's how we optimize. The chemical etching has high selectivity. Okay, selectivity means this will be high. Okay, the vertical component can be removed very fastly. And the physical etching like sputtering, ion milling has low selectivity. It will just physically let's say you have this masking material film and you put it in a beam of ions coming towards it, then it will remove everything, sputter everything. So that's what it meant, selectivity. Then there is something called anisotropy. So when we put it in a solution, so you have the ratio of horizontal etch rate to the vertical etch rate. If both are equal, as I said, everything will go off. So that is one. So we don't want, if you want to make pattern, you need something anisotropic 0. But in real case, it won't be possible. It will come somewhere around 0.5. So it's so here if you see, it is keep on etching. So that you call undercut. Yeah. So yeah, now I just want to say the limitations of wet etching. So in our lab, wet etching is limited to pattern size of 2 micron or larger. So and it is isotropic, which will result in slope walls. So since it needs a lot of rinse and dry steps, okay, so much of pre-cleaning and post-cleaning process are required. And obviously most of the chemicals are all gases are all hazardous. Okay, and it leads to a lot of contamination. So basically, if you see silicon, it has a band gap of 1.12. So if you put it in any etchant, let's say there is a gold. So gold is used as a pad. So if you use gold will be etched, and this metallic impurities will kind of occupy the mid gap states. So which will act as a recombination centers. Okay, then recombination centers on the device level you call minority carrier lifetime killers, they call. Okay, so they all will come in this contamination wet process. Yeah. Then So they won't, resist wafer bond while doing bonding. So it's failure of the resist wafer bond, which will cause undercutting. So this is one more limitation. So that's why we have to go for dry etching. Nowadays most of the industry they use dry etching unless until it is a cleaning. Okay, so that's what I meant. So basically, physically dry etching means create plasma and keep hitting. Okay, so with some excitation energy, more excitation energy. Okay, then chemical dry etching means you make the chemical to react. So most of them, so they are ionized, and here if you see there is this a fluorine based gas which is dissociated, and it will form the radicals. So the radicals are highly reactive, even for human beings also. So they will react with the silicon and form the gases. So basically, whatever you see here, so it's a chemically, etch. Means instead of liquid, you use gas to etch. So that is by using the radical chemistry. So here all physics, like hit with a heavy atom with higher acceleration, then it will lead to a lot of damage and all. So a lot of damage will come. So in respect to all this, most of these tools are kept in vacuum. Okay, so almost at 100 millitorr kept. So by combining these two, so people have come up with something called reactive ion etching. So basically you use both of the techniques, like physical and chemical, so create such kind of directional etch. So that is what in industry most of them use this. And there are this results from IIT using reactive ion etching tools. Okay, if you use SF6 on silicon, so it has created so basically this all is silicon. So there was a mask before, then you etch, so you get profiles like this, 5 micron lattice, and yeah, so etch rate is around 3 micron per minute, all that. So basically, when you are using etching tool, you have to ask which gas and how much power and how much time it will take. Okay, based on that, you have to. Then there is this germanium. So here, so as you can see here, SF6, here CF4. So basically, our fluorine based. Fluorine is fluorine ions are or radicals are highly reactive. So you need to dissociate and ionize them. So there. Hello. Can you turn the mic off? So then DRIE, so deep reactive ion etching, the people who are working on MEMS, let's say they want to create accelerometers, gyroscopes, all this, MEMS structures, microelectrical mechanical systems. So they all will use, because this can go deeper. It can etch whole wafer and make whole lot of, the wafer and come on the other place. Here, this figure is one of my friends. So what he did, so he want to increase the surface area for the solar cells. So what he did, he put this polymer beads and he put it in this system. So it has formed this, grooves. Okay, so it has formed this longer silicon nanorods kind of structures. But if you see in the corners, you have this grooves. So basically, why that grooves are coming means it uses this DRIE uses one process called Bosch process. So basically, it uses multi-pulsed multiplexing technique. So basically, it keeps switching between the gases. Let's say it will pass 6 gases. It pass C4F8 for 6 seconds, and it will turn off, and SF6. So SF6 is reactive with silicon, but the C4F8 will kind of passivate the surface. So basically, let's say you have a trench. Okay, now SF6 will etch. Then before before attacking, C4F8 will come and cover the side walls. So that's how you make the deeper trenches. So this is one of the techniques. So okay, yeah. This is what I want to show in etching. Then other one is oxidation. So yeah, so let me push it. So we have different oxides. So thermally grown oxides. So based on our understanding, we go for these oxides. So one is chemical oxides. Like, so when you put it in any oxidizer like HFO2, you can get this kind of oxides, and these are gate oxides, which is used for device MOSFETs or tunneling oxides in the flash memory, all that. Then pad oxides, for lithography, all that we use. So if you see why thermal oxidation, it is a really excellent oxide because it grows from the silicon, its own native oxides. That is what made silicon very successful. Okay, and it can be easily etched in hydrofluoric acid or buffer hydrofluoric acid. Okay, and it has great interface properties. So that's why we are going for oxide. Then, so which one is better? Means dry oxidation. Okay, but it can't go for small higher thickness till 200 nanometers only. It can grow, but wet oxidation, it is faster. Then charges and traps in the oxide okay, so if you grow oxide, so you will have all this. So this will lead to the threshold voltage shift in the oxide. So basically at the interface, you'll have interface states you call like dangling bonds. So here you have fixed oxide charges. So this is what if you grow oxide, this is what you have. Even in the thermal oxide itself, it is like that. If you go with this kind of deposit oxide, the traps are more. So it is best, people go with the thermal oxide, but you have to see what is the process and all. And it can be grown using the typical furnaces. Okay, so you keep the wafer, so you push the temperature to 800 to 1100 degrees, and you introduce the gases, so it will grow. And these are rapid thermal processing chambers. So you keep the wafer and you give high temperature for shorter time, not like here we have to give 20 minutes, 30 minutes based on the thickness. Here maximum you can waste 1 minute on that. So that is what I want to talk about oxidation. There is another thing called an implantation. You selectively introduce the doping atoms. So yeah, basically ions are directed onto this wafer through all this stuff. Okay. Yeah, these are some ion trajectories. Once you dope, so they go in different directions. Okay, this is the silicon depth if you consider. Okay, then whenever you are specifying, so what and all you want to implant. So these are the few parameters. So what are the implant species? You have to boron, phosphorus, arsenic. Then energy. What is the energy? 30 kV, 20 kV, all that. Then how much dose, channeling, all this. Channeling is nothing but so since silicon is crystalline, if you directly do 90 degrees implantation, they will come out of the crystal. That's why people recommend you to go with the 7 degree or 4 degree tilt. So example, arsenic 25 keV. So this is the dose. Okay, and yeah, the rotation. So basically, it's just for doping only. Okay. Then there is this thin film deposition. It's very important. Okay, even the metal deposition can be considered as thin film deposition. There are a few ways you can deposit the film. One is a physical way, means physically you take the target. Here the target is something called any metal or any material that you want to deposit is called target. So what you want to do, you want to heat the substrate or you want to heat. So heating is something called evaporation. Okay, then if you heat, you call it as sputtering. So this is what and chemical means you introduce the chemical gases. You break the chemical gases bonds by giving energy in the form of thermal, okay, or plasma. So you break the bonds and you make sure use the vacuum system, make sure that all will fall on the substrate. So that's how basic overview. So this is what I'm saying. Thermal evaporation. You keep a target here, just heat it, so it will evaporate. So this will be. So this all can be achieved using this kind of mostly Belge or designs they call. So you have your substrate here, and you have your, let's say, gold. So you heat it, and they all will go evaporate, and there will be thickness monitor and all. So basically, this there is something called mean free path. So you pump the vacuum in such a way that the particles won't be scattered; they will come exactly onto the substrate. So that is what thin film. Other sputtering technique I was talking about. You introduce the inert gas, argon gas, and break them. So create plasma and give the potential difference and accelerate these ions towards the target. So then it will remove them. Then give the voltage to bring those charged ions towards the substrate. This is called sputtering. So these are the tools which you have in ITBNF. So there are here there are two takeaways. So all the evaporation technique, go with the line of sight deposition. Means, let's say you have a pattern like this. If you deposit, it will deposit here, 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 here. Sorry, here it didn't get deposit. So you will have like this. So conformally, whichever shape you have, it will just go with that. So that's what I want to conclude. And when it comes to thin film, so you have this, conventional CVD, nothing. As I said, you have gas, break the gas, and try to, deposit on the surface. So here PECVD, okay, use plasma, break the bonds, and you get the film. So in the similar way, you have this ALD. So ALD is something different. So it works on something called chemisorption. So basically, you will have this organic precursor, metal organic precursor. You purge them, then then you make to react with the surface, and that's how the film will be going, atomic layer deposition and all. This is one of the techniques. So coming to clean room technology. So yeah, this I think we all know this. We are the contaminants. When you are working on the device, even the sneeze also can go and create the short circuit between the two metal wires at the nanoscale, and people say that. Okay, so basically, as I mentioned, the size of the airborne particles are of the same size of the device structures. That's why we have to have clean room. Okay, so basically these are all the sources of contamination. That's why we use filters to clean out. Okay, so and this is our human hair SEM image. Okay, so this we have to wear the head cap, face mask. Okay, all that, so that there should not be any contamination onto our device. This is for our device. Okay, let's say if there is a mask. Okay, I want to do lithography for the gate edge. Let's say by mistake, my human hair fall on this. So then if I perform lithography, I will get pattern like this only. So this will short all the gates. So that's what I want to show. Then, okay, and this is what the clean rooms. So you will have this HEPA filter, okay, high efficiency particulate air filter. Nowadays, there are air purifiers in the market. They're also using HEPA filters. So basically, you see, so the air is like, circulated through this, and it keeps circulating fan and system and all, okay. So you will have HEPA sealing, and you will have optical floor. You will have the, all this perforated floor will be there. So air will go through it, and it gets filtered and all. So this is how the air handling unit, will work inside the clean rooms. Okay. And yeah, this is just a schematic. In the HEPA filter, they usually use the glass fiber. So this will kind of trap the particulate, matter, dust, so that it won't. The clean air will be coming through this. So these guys will trap the particulate matter. Then okay, these are the different clean room layouts where you have. So you have a big clean room. Then this will be surface area where they will keep all the gases, cylinders, everything, and you keep all the equipment. Otherwise, you keep service chases differently. Okay, and you place the equipments in this. Here though, you keep equipment everywhere, so you can't control the cleanliness properly. So, and this is one more clean room type. Okay, And so basically in IIT Bombay, we have something called class 1000 and class 1000. But if you go to industry, you have class 1. So as you can see, let's say class 1000. So the particles which is of, 0.2 micron, greater than 0.2 micron, if they are 237, then it is, class 1000. So it's like, so normally, so this, so it depends on the particle size. Or you can say class 1000, you say the particle which is of 1 micron, if they're 8, it is class 1000. It's like that. So basically this all ranges of particles will be there and it can be calculated using this. So yeah, this is all about clean room. So these are some resource pages. Okay, you can watch. And yeah, thank you. Any doubts?
Thank you, sir.
Yeah.
There is one question in the chat box.
Yes. Just
a minute. One question from Dr. L. Saravanan.
Okay.
How can we decide to use it? Okay, no, that is in the last, actually, last session. Okay. How technology node value is decided? Okay, that is a question from Vijay Lakshmi Kumar.
So technology node, so as I said before, so they kind of changed the definition. Yeah, this one. So basically there is something called Dennard scaling. So basically this technology node can be decided by equipment people who will design the equipment, like the lithography machines and the deposition chambers and etching people. So they all will decide what is that, basically, yes, theoretically and simulation wise, people can do how much ever smaller they want, but whether physically what are the limitations on the industry perspective is a lithography tool and all. And after 1990s, so there is nothing like just a second, I can show one slide. So I think I hided this. So if you see here, so basically, so there is first so process and lithography innovation, they kind of, so as I was showing in lithography, so this also will push. Okay. And other thing is the scaling means, so you have to scale the voltage, oxide thickness, I mean you can call it as a 3D scaling in all the dimensions. So make sure that you get the same electric field. So I can say the process and lithography innovations and the electric field scaling or voltage scaling by keeping the same electric field also can contribute to this node names, all that, like, because we want higher drive current. Means what is a good switch? High on current, low off current. So there should not be any, like, if I want to turn off, it should not it should not let any current into the system, so into the MOSFET. So but is it ideally possible? No. So there will be always some leakage. So that's what will drive. Good switch means the ion to I off ratio should be greater than 10 power 6. That is called good switch. So that will always drive the process engineers and the lithography people. Okay. So make sure that I have the same ion current. So does it answer your question?
I hope so.
Okay. Yeah.
Okay. So
you muted all of them. Okay.
There is one more question from Dr. L. Saravanan. Sir, how do we identify the need of classroom facility before installing the device fabrication and for characterization facility?
Okay, so characterization. So once you make the device, So before going for the characterization, you cap with some material called silicon nitride. So basically, once the device is made, let's say, okay, not here. So I can show here. So once the device is made, so everything except, for the metal contact is capped with something called, dense materials like nitride, and there will be opening only for contacts. So you can have, class 10,000, just it can be achieved using air conditioners. I mean, you might have seen this intensive care unit in hospitals. Similar like facility can be used even for characterization rooms. I mean, through air conditioner, in the air conditioners also you will have this HEPA filter, so that will be sufficient because they're already capped. I mean, they're already covered by the passivation or encapsulated material. So so that is one way. But if you are working on new materials, yes, you have to be careful. There is something called desiccator. So once let's say you want to do inline measurement, which may like you want to do some measurement, so you have to keep that in desiccator, vacuum it, take it to the characterization lab, measure there. Okay, yes, there is some access to the contamination, but yes, research, yeah, you can't avoid. But in industry, once the wafers are properly fabricated, it is properly capped, encapsulated, so that we can only do characterization or probing. So you don't need great clean room for characterization. But when it comes to this unit processes, you need to have a pretty clean room, class 1, because because industry is all about yield. How many good chips out of total chips? Because it's a business for them. So I mean, we want less bad chips than good chips. So yeah, can we be able to sense how much particular matter in our area? Yes, we can sense using there are meters, particular air meters, so we can sense. So nowadays, but could we control, purify in the time of emission from vehicles industry? Yes, we can control, but it is expensive. You have to keep changing the HEPA filters very frequently. In our lab here at IIT Bombay, they used to change every 2 years, but the cost is very high. So basically, you have to, there is a trade-off between cost and the quality of the air. Yeah. Okay. Thank you. Yeah. I showed some filter, right? Yeah. Yes.
Okay.
Yeah. Yeah. I think I was on time.
Yes, sir. Yes, sir. Meanwhile, I have one basic question, that is, how NMOS and PMOS fabrication process are different, or both are same?
Okay, so here in the first one I've shown here. Yeah, here if you see, the fabrication is same. But
Okay.
what you have to do, so let's take one big wafer, let's say P type. So what they do is they create N well in that. So there will be P well and N well. So first they mask, P type and do implantation, P type implantation. Then they mask this area and they do. So on the same wafer they do that way. Like
Okay, means in terms of substrate only, I have to just select the substrate.
Yeah, so I showed some process called implantation, right? So on the same substrate, you use this implantation. So you use implantation and create that P well or N well first. So let's take P silicon, then you create a well. So you mask one area, there will be P, and you create N well, then you do all the other process same.
Okay, so most of the time we are using NMOS. Okay, is it correct?
Okay.
Okay, PMOS.
No, I mean,
how
for
how
CMOS,
it is depend whether we have to use NMOS or PMOS?
So basically, I mean, NMOS, see, for silicon, we have to use both. For, let's say, it depends on the functionality. If you want to use just as a switch, NMOS is fine, because NMOS is electron rich, so electrons has higher mobility, so that's what they are faster. For PMOS, the most of them, I mean, the holes will drive the transistor, so you need twice the size of the NMOS in order to achieve such kind of performance. So basically, the whole mobility in silicon, it's a material property. Electron mobility is higher, hole mobility is lower. So that's what people prefer NMOS. But for digital digital design, or digital blocks, like let's say ALU, let's say half adder, full adder, all this, so you have to use CMOS both. I mean,
Okay.
PMOS and NMOS together, and even for NAND or all that, whatever, all the digital can be achieved through CMOS only. We can't use NMOS alone.
Okay. Okay. Thank you, sir, for your explanation. There is one more question, last question from Rama Shankar. How we can magnetize diamagnetic materials via fabrication methods?
Okay, the diamagnetic materials. Magnetize. I don't know, man. I mean, see, I'm not sure. Ferro,
Oh,
cobalt, nickel, they are ferro. Yeah, you can transfer the torque into that using some oxide, but from the ferromagnetic to die. But via fabrication methods, I don't have any other idea. Maybe I can send you some reference. The spin people can be able to answer it. Uh, mm, yeah.
okay. Okay.
I
So,
mean, all the these materials can be deposited using sputter technique. Okay, sputtering is the technique where we can deposit this all magnetic materials. So the people who are working on the spintronics, so they deposit ferric, cobalt, nickel, all that. So using this sputtering tool, I think that may answer it. Sure. The same thing could be for diamagnetic also. Yeah, Mr. Yuvraj, saying something.
oh, oh, no, no. Just thanks to understand the complete fabrication process. Means we have studied through, means only through the textbooks only, but we never seen the process in detail. So this is a great opportunity basically to understand semiconductor fabrication process. Thank you.
Yeah,
Thank you for the opportunity. Now I invite Doshi ma'am to express the vote of thanks. Doshi ma'am,
yeah.
over to you.
Yes, yes, yes. I'm there just waiting. The session was really very interesting, sir. Uh, we are really fortunate. Like you started with the history to understand why semiconductor industry is there in India. And really, we are fortunate. And the next batch, in fact, is more fortunate to go for career in this.
Yeah.
And it was wonderful session. So like we never knew what practically how it happens because we were just only having the process of how the doping goes on and intrinsic and extrinsic and all the
Mm.
different terms we understood. But then today we thoroughly went through all the things, and we are happy that we are getting this opportunity in India, and we'll be doing great with all the budding engineers now I expect to go for. So here I go with the vote of thanks and sincere gratitude to Dr. Prem Sai, our esteemed guest of honor for today's ATAL's Faculty Development Program. Your expertise as staff engineer to device design at IVP Semiconductors with a strong focus on innovation in power semiconductor device design, sir, greatly enriched the session. Really, hats off to you, sir. The lecture on introduction to semiconductor fabrication and clean room technology was the best part because we only knew the theory part, and this was the only practical part where we understood the fabrication, how it goes on. So it was strengthened by your rich hands-on experience in fabrication processes, then process integration, electrical characterization, and TCAD simulations. Your valuable contributions to the semiconductor workforce development at SemiX and the extensive work at IIT Bombay's nanofabrication facility provided participants with very rare industry academia insights. So, on behalf of the organizing committee, we sincerely thank Dr. Prem Sai, for your time, expertise, and inspiring interaction with the faculty, because it is 1 or 0. Either you like it or you don't like it. And I saw that everyone was liking it very much. So thank you once again for like accepting the invitation and sharing your expertise on this. I thank Prem or Pranav also for helping us
Yeah,
to find a diamond like you to help us understand the fabrication process,
yeah,
actual fabrication process. And in time you finished. That was again one more good thing.
yeah.
And but then we can have one more session in which we can detail different
Yes,
parameters of
yes.
the
Yeah.
fabrication.
Yes,
We
yes.
can
Uh,
go for
This
that
is just
also,
a
sir.
tour.
I have
Yeah.
a small request. That is, if you have a complete video of this fabrication process, so if you are able to share with us, so we can share with participant also.
Yeah, yeah. I shared the slides. So, okay. On
Okay.
I
So
mean,
can we
yeah, you can
share?
get. There are so many videos. I mean, if you want, I can share. I shared one link, the Intel. Well, I think you will get a lot of insight. Uh,
Yeah.
uh, I mean,
Yes, sir.
yes.
Okay, sir.
Okay, sir.
So
Okay.
thanks. Thank you once
Yeah.
again. All the participants for 106 participants are still there.
Oh,
It
yeah.
shows that, yes, we had some good audience also.
Correct.
So
Okay.
thank you once again,
Thank
sir.
you.
Thank
Thank
you,
you.
Good
sir.
Bye
night.
bye.
Bye.
Good night.
Bye.
Thank you,
Good night.
sir, for your wonderful session. Okay.
Yeah. Thank
Thank
you.
you.
Thank
Okay. Bye.
you.
So we can take a screenshot if all of us can.
Okay.
Uh,
Okay. Turn on the
Okay.
camera.
Oh,
Yeah.
okay.
Prakash sir, you're taking?
Yes, ma'am. Like one.
Okay.
Just a minute. People are
Yes.
just okay.
Yes. Let all of them be the part.
From tomorrow onwards, we will do at the start and at the end of the
Yeah.
session.
At the
Okay.
end, yeah. At the end, we'll ask everyone
So we are just
to.
missing due to this question answer session. Okay.
No. But then today in time we finish, so
Correct, sir.
it's like we can have this chance.
Yes, I have taken one screenshot. Okay. Thank you.
Okay, sir. Thank you
Thank you
once
all.
again.
Thank you.
Bye, all the participants.
Thank you.
Let us meet tomorrow, the last day.
Bye bye.
Okay, so I'm ending the session. Okay.
Yeah, sure.
Okay. Thank you.
Okay.